Good afternoon, sir.
Hello, good afternoon.
Yes, good afternoon. Please keep the cameras on.
Yes. Aishwarya, Hareep, Ashaf. Okay. Keep the cameras on throughout the session. Also, a lot of you haven't sent the class notes, so please make sure you're sending the class notes soon after. Okay. Okay. So yesterday we have stopped at spring force, right? So spring force is a type of conservative force we have discussed. And conservative force, what are the properties of conservative force? Uh, Anyone? What are the properties? Yes.
Release does not depend on the path taken.
Yes.
It only depends upon the initial and final positions.
Initial and final positions. One more point. Anything else?
Does not depend on the path taken.
Yeah, that is true.
The
One
work
more.
done is the same.
Work done is the same, irrespective of the path taken. That is true. One more, like if it's a cyclic process, work done is
0.
zero. For a conservative force, work done is zero if it's a cyclic process. For example, if you are lifting this object to a height h and you are bringing it to the same position, that process is called a cyclic process. You are bringing it to the initial position. So in that process, if you're considering the work done by a conservative force, in this case, if you're talking about gravity, so the work done by gravity to take it up is minus mgh, and work done by gravity to bring it down is plus mgh. So total work done is minus mgh plus mgh, that is equal to zero. We have seen this previously. Also, we have seen that for a non-conservative force like friction, the total work done in a cyclic process may not be zero. Like we have seen in the case of friction, it was 2 times F into the displacement, friction force into displacement. Okay. So coming to spring force, which is again a conservative force, we discussed a few things in yesterday's class. So we saw that when you actually stretch or compress a spring, displacing it from its mean position, you are actually creating a restoring force inside the spring. A restoring force develops inside the spring, trying to bring it back to its mean position, okay, or the position of minimum potential energy. So we have assumed the potential energy to be zero at the mean position of the spring. And when you are stretching it, you are storing some potential energy, which we will calculate. We will try to calculate that just like we did with gravitational force. We have a different expression here. We'll calculate it. But now when you apply a force, when you stretch it, a restoring force develops inside the spring, trying to bring it back to its mean position. Or when you compress it, reducing its length, moving again away from its mean position, again the restoring force will try to bring it back to its mean position. So anyways, the restoring force is always proportional to the displacement. Okay, restoring force is always proportional to displacement, and the restoring force is opposite to the direction of displacement. If the displacement is done towards the right, if you're stretching it towards the right, the restoring force is acting towards the left, trying to bring it back to the mean position. If you're compressing it towards the left, the restoring force is trying to bring it back to the right, to the mean position. So anyways, the restoring force is proportional to minus x, minus because of the same reason. And that can be written as F is equal to minus kx, where k is the proportionality constant, or we call it spring constant in this case. So we have seen what spring constant is. K, spring constant k is equal to F upon x in magnitude. And you can see that the spring constant k, if the k value is very large, that means force, a restoring force developing for a certain displacement is very large. So that means we call the spring as a stiff spring. Okay, if the restoring force developing for a certain displacement is very large, we say the spring is stiff. If it is very small, we say spring is not as stiff. It's very loose spring. Okay, so these points we have already discussed. Yes, please keep the cameras on. Everyone, cameras. Farhan, yes. Zaid. Okay. So we will look more into the restoring the spring force today. Okay. All right. So first, do one thing. Let's write few points regarding this. Okay. Also, you can observe one thing here. Like I've told you, the restoring the spring force is given by F is equal to minus kx. So can you tell me whether this is a constant force or is this a variable force? What do you think? It's a variable force, right? Why? Because you can see clearly that force is proportional to displacement. So more farther you take the block away from the main position, more stronger will be the restoring force. So clearly you can see that the spring force is a variable force. Okay, spring force is a variable force. And we need to calculate the work done by this variable force using the formula we have discussed. Variable force. Okay. So how do we calculate the work done here? So we can see that the work done by a variable force for a short displacement dx, for a short displacement dx, okay, the work done by the spring force will be small work done by spring force will be uh, dw is equal to fs dx. Okay, dw is equal to fs dx, or you can say this fs can be replaced with kx dx. That is the small displacement in magnitude. Okay, small work done in magnitude. So if you calculate the total work done, suppose I am moving the spring from, let's say, suppose this is the spring, this is the mean position, let's say, this is the mean position, x is equal to 0. Let's say the block is right now at this point. So this is, let's say, the initial position that the block is at right now, xi. Suppose I'm shifting it to a new position by applying a force on it in this direction. I'm shifting it to a new position, x subscript f. Okay, so what is the work done during this? To calculate that, we can't directly use f dot s and say that, because the force is not a constant force, it's a variable force. Okay, so the work done will be equal to kx dx, that is the small work done for a very short displacement. Let's say we are talking about a very short displacement here. For this short displacement, the work done is equal to kx dx, where kx is the spring force and dx is the small displacement. Now we need to integrate it. That's how we calculate the work done in a variable force. Okay. One second. Yes. So the total work done is equal to integral of dw. This is equal to integrating kx dx from xi to xf. xi is the initial position of the block and xf is the final position. So we need to calculate the work done by the spring force here, work done by the spring force. So this is k taken outside. What is the integral of x dx?
X square by 2.
Yes. So integral x dx is x square by 2. So k times x square by 2 from xi to xf. So this is half k, half taken outside, then putting the upper limit xf squared minus xi squared. So this is how we calculate the total work done. Now, if you are taking the initial position to be xi, I mean, if xi is taken to be the mean position. Okay, if the initially the block was at the mean position, so the work done in displacing x through the spring through a distance x will be equal to half k x square. Okay, so this is the work done by the spring force. Work done by the spring force. Okay, so you have to remember this formula because it's a very useful one solving questions. So you have to keep this in mind. Please keep the cameras on, Aishwarya.
Sir, I actually joined late, so what did we do so far?
So we just calculated the work done by the spring force. That's all.
Okay, sir. Okay.
Okay. Now in the same formula, look at the same formula. In the same formula, if initial and final positions are same, that means we are talking about a cyclic process. You can see that since spring force is a conservative force, you can see the work done by the spring force in this case will be half into k into xi square minus xi square. So this will be equal to 0. So work done by the spring force will be 0 if you're talking about a cyclic process. We're talking about a cyclic process where the initial and final points are the same. Okay, so note down few points regarding spring force now. This is the work done by the spring force. First point. Spring force is position dependent. Position dependent. Spring force is position dependent, which is why we say spring force is equal to minus kx. It depends on the value of x, spring force. Second, work done by a spring force. Work done by spring force. A F there. Work done by spring force Okay, so work done by the spring force, if the block attached to the spring is pulled from x initial and is allowed to return to x initial is 0. So work done in this case is 0. In bracket, you can add cyclic process. Third, work done by spring force depends
Sir, in the first point, force of the spring is equals to minus kx. So what does k represent there?
spring constant.
Okay.
Work done by the spring force depends only on initial and final positions. Final positions. Okay. Now, whatever work is done by the external force on the spring, that will be stored as the potential energy of the spring. So if you are doing the work done, suppose you are stretching the spring through a distance x, so you're storing potential energy. So we can say the work done by external agent will result in increase in potential energy of the spring. Potential energy of the spring, and that potential energy is this same. I mean, if the spring force is minus kx, the external agent has to do a kx work in the opposite direction to store the potential energy, just like we did with mgh. When you do mgh work to raise an object through a height h, so that is, you are storing potential energy there. Similarly, the external agent doing work by applying a force of kx in the direction of displacement. So the work done will be half kx square if initial position is the mean position itself. Okay, so this work done gets stored as the potential energy itself. Okay, so this is the potential energy expression for spring. So if it is not starting from the mean position, then you have to add x final square minus x initial square.
Points. Just a minute.
Sorry.
Can you show the point before this?
Yeah. Yes.
Work done on forces. Oh, okay.
Hmm.
Got it. Got it, sir.
Okay. Okay, so let's try to
Sir, 1 minute,
solve.
sir.
Okay.
Yes, sir. Okay, finished.
Okay. So you can try solving this question. Yes.
So what is the answer?
Have we got the answer?
So is it like in mathematical expression or normal just?
Mathematically, we have to solve it. We have to try to reach to it. So here you can see the two springs are having force constants K1 and K2, where K1 is greater than K2. Clearly, K1 greater than K2 means which is more stiff. Which is more stiff.
K1.
First spring. Clearly, K1 is larger means more force is required to stretch it by the same distance. Okay. Now suppose if they are stretched by the same force. In the question they are saying if they are stretched by the same force, that means force will be equal to minus K1 x1, and in the second case f is equal to minus K2 x2. Because the force is same, so I have taken the same f here. Okay, so K1 x1, I can write it K1 x1 minus K1 x1 is equal to minus K2 x2 because the force is same, stretched by the same amount of force. Or I can say K1 by K2, K1 by K2 can be written as x2 by x1. K1 by K2 can be written as x2 by x1. Okay. Now we need to calculate the work done, which work done is greater, which you can just take it by the ratio. So work done in the first case divided by work done in the second case by the spring. Work done formula is half K1 x1 square by half K2 x2 square. So we can compare now. So this is K1 x1 square by K2 x2 square. Okay, so we can replace this x1 by x2. This can be written as k1 by k2 into x1 by x2 whole square. So x1 by x2 whole square is x1 by x2 whole square can be written as k2 by k1 whole square from this, right? So I can write it as k1 by k2 into k2 by k1 whole square, or you can cancel out one of the case, one of the k1 and one of the k2. So you can write it as k2 by k1. Okay, because of the square. So work done by in the first string by second string is equal to k2 by k1. So, or I can write work done by 1, the first string is equal to k2 by k1 into work done by 2. So is k2 by k1 larger than 1 or is it smaller than 1?
Smaller than 1.
Because k1 is greater than k2, right? K1 is greater than k2. So you can clearly see that this value is less than 1. Less than 1. So work done by 1 is the fraction of W2. That means clearly W2 is greater than W1. This is how you can reach to it mathematically. Okay.
There's another way, right? If K1 is greater than K2 and if the force is same, that means X2 is greater than X1. So if X2 is greater, then work 2 will also be greater. Can we just deduce it like that?
You can think of it like that also. No problem. Yeah.
Hmm.
Easier.
So can you show the solution?
Sorry.
Can you show the solution? Can you zoom
Yeah.
out?
Yes, yes. Those who have completed can try the second one.
Sir, if you stretch the spring, then what formula will we use for that?
Uh, no, that depends on what do we have to find. Like if you're talking about the force, restoring force, then it's minus kx. F is equal to
No,
minus
like in the
kx.
second one, they are stretched by the same amount. So,
Stretched by the same amount means the displacement is same. X is same.
okay.
So
X
you
is
can
same.
think
Okay.
X is same, stretched by the same amount, same length. So Ian, you also, I think you have answered it correctly there. Okay, uh, so you can think of it like this also in the first case, like K1 is greater than K2, right? K1 is greater than K2 means the first spring is more stiff. First spring is more stiff. More stiff means if the force is same, the work done will not be as much because the displacement is less, right? Because you can see the K2 is not as stiff, so more work can be done on it if both the forces are same. So if the force being same and the stiffness is different, so K1 is more stiff. K1 is more stiff, so you can think of it like the displacement is very less there. So the work done will be more in the second case because it is more free. Okay, so try the second one. If they're stretched by the same amount. So completed can try the second next question. This part is direct, right? If they're stretched by the same amount, if you calculate the work done in this case, compare work done 1 by work done 2. So this is equal to half k1 x square by half k2 x square. I don't have to write x1 and x2. This both are same, so they cancel out. So this is k1 by k2. So I can say work done by 1 is equal to k1 by k2 into w2. Okay, so clearly this value is greater than 1 because k1 is greater. So that means the work done by 1 is greater than work done by 2. Okay, so try the next question. Yes, Areeb, can you tell me how to calculate this? Length of the steel wire is increased by 0.5 centimeter when it is loaded with a weight of 5 kilogram. So calculate the force constant of the wire and the work done in stretching the wire. So you have a steel wire. You can think of it as a spring itself, because if something is getting stretched, there is a restoring force developing inside it. So if there is a steel wire fixed here, let's say, and it is loaded with a weight of 5 kilogram, loaded with a weight of 5 kilogram. So that means if it is loaded with a weight of 5 kilogram, that means the force acting in this downward direction is how much? How much is the force acting here? That is the applied weight of this block that is trying to stretch it. So this is the force here is equal to mg, that is 5 into, let's say, g is equal to 10. So 50 Newton will be the force applied here. Okay, so restoring force will try to balance it because the steel rod is not breaking, wire is not breaking. So the restoring force is balancing it, equal to it. Okay, applied in the opposite direction. So we can say the spring constant is equal to F by X, where F is the restoring force, which is equal to this 50 Newton applied, and X is the displacement or the stretch happening. So you can see that the displacement is 0.5 centimeter according to question. So 50 Newton by 0.5 centimeter, 0.5 centimeter, so 0.5 into 10 power minus 2 meter. So 50 into 10 power 2 by 0.5. Okay, so 0.5 into 0.5 into how much is 50? 0.5 into
100.
100. 0.5 into 100. So 100 into 100. So this is 10 power 4. Unit is Newton per meter. So this much Newton per meter is the spring constant. Spring constant. Okay. Similarly, in the
Sir, the
second,
work done 0.0125 joules.
yes. So work done can be calculated again using the formula. Work done is equal to half kx square is equal to half k is 10 power 4 into displacement is 0.5 into 10 power minus 2 whole square. Okay, so this is 10 power half into 10 power 4 into 0.5 square, 0.25 into 10 power minus 4. So this is 10 power 4 into 25.25. So 25 100 into 10 power 10 power minus 4 by 2. Okay, so 1, 2, 5, 0 into 10 power minus 4. So this is 0.125. 0.125 joules is the answer. This much work is done in stretching the wire. Yes, keep the cameras on, everyone. Manan, Aishwarya.
Sir, how did you find the X value?
X value. X is given here. X is the displacement from the mean position. So X is like 0.5 centimeter. So length is increasing by 0.5 centimeter. It is given. Okay.
Sir, can you scroll down a little bit?
Okay. Yes, please keep the cameras on. Shad, Zaid, Aishwarya. So those who have completed can try this question. Spring of force constant 24 Newton per meter is resting on a frictionless horizontal surface. A force of 10 Newton is applied on the block of mass 4 kilogram at one end of the spring. What is the speed of the block when it has been moved through a distance of 0.5 meter? Yes, so how do we solve it? So the question says spring is given with spring constant 24 Newton per meter. It is resting on a frictionless horizontal surface. A force of 10 Newton is applied on the block of mass 4 kilogram at one end of the spring. What is the speed of the block when it has been moved through a distance of 0.5 meter? So when you do some work on the spring, there is no dissipative forces here. Means there is no non-conservative force here. There is no friction. So we can see that whatever work that you're doing has to be conserved. Okay, so that gets transferred as either the kinetic energy or the potential energy inside the spring. Okay, so we can see work done is equal to work done, we can calculate it. What is the value of work done here? Work done is the force is given, displacement is given, right? So move through a distance of 0.5 meter. So work done is force into displacement. Force is 10 Newton. 10 Newton into displacement is 0.5. This is equal to kinetic energy is half into mass into V square. Mass is 4 kilogram into V square, velocity square. So we have to calculate that velocity plus potential energy of the spring. What is the potential energy of the spring? Fida, can you tell me what is the potential energy of spring?
Sir, MGH, no?
No,
No.
not MGH. MGH is the potential and gravitational potential energy. So, Rehan, can you tell me what is the potential energy of spring?
Sir, MGH.
No, no, no. That is gravitational potential. We have just now derived it. The spring potential energy. Vijayasree, can you tell me?
Half kx
Or
square.
is it half K into 2?
Not half k into 2, half k x
Sir,
square.
I was not there, sir. I was like, for the past 20 minutes here, there was no current.
Okay. I think this is before that. This is in the initial 10 minutes. Okay. Anyway, so this is half kx square is the work done by the spring force. See, this work done by the spring force itself is the potential energy. See this. This is the expression for potential energy of the spring. mgh is only the potential energy in the case of gravitational force. Remember that. So this is the potential energy of the spring. If you talk about electrostatic force next year, you will see it has a different potential energy. So potential energies can be of different forms. So here you have to calculate the potential energy. Potential energy is equal to half k x square. Okay, you have to substitute the values here. 0.5 into 10, 5 is equal to half into 4, 2 into v square plus half into k is 24 into displacement is 0.5. So 0.5 squared. So 5 is equal to 2v square, 2 into 12, 24, 2v square plus 12 into 0.5 square, 0.25. Okay. So 2v square is equal to 5 minus 12 into 0.25. Okay. So 5 minus, how much is this? 12 into 0.25.
Sir, can you write 12 into 1 by 4?
We can write it as like that also.
So it will be 3.
That's good way to write it actually. So very good. So 5 minus 12 into 1 by 4, that is 3. So it is 2. Okay. So 2v square is equal to 2, v square is equal to 1, v is equal to 1 meter per second is the answer. So you should know why are we using this equation or why are we able to use this equation?
V will be root 1, right?
Root 1, which is 1 itself. Okay, so we can see there is one thing here. Why did we use this conservation of energy? Like, how did we know that work is entirely getting transferred into kinetic energy plus potential energy? Why? Because there is no dissipative energies here, dissipative forces here. So basically, you can see that there is no friction here where the energy can be lost. There is no other way to lose energy, or heat energy is not lost in the form of heat also. So entirely whatever work is done should be getting transferred. The energy should not go waste. So it is getting transferred. It is getting in the form of kinetic energy and potential energy. That's how we reached to this expression. So conservation of energy is actually a very useful form of, a way to proceed in many situations. Try to do this. Farhan, is it clear? Hello, Farhan, audible? Aishwarya, is it clear? Any doubts?
No, sir.
Okay. Hamza, any doubts?
No, sir.
Okay. So,
Sir, compression means we can take it as displacement, right?
yes, definitely. If the spring is, this is the mean position, then if you're compressing it like this, so this is the new displacement from the mean position. You're compressing it towards the left. So a solid of, okay. Yes, a solid of mass 2 kilogram moving with a velocity of 10 meter per second strikes an ideal weightless spring and produces a compression of 25 centimeter in it. Calculate the force constant of the spring. So you can see that solid is moving with velocity 10 meter per second. That means it is moving with certain velocity means it has certain kinetic energy. Okay. So with this kinetic energy, it is striking the spring, and the spring is an ideal spring, weightless spring. You don't have to consider its mass, or there is no friction given here. Okay. So the entire,
About 30 to 100 Newton.
yes, 3200.
Yeah.
Okay. So the entire entire kinetic energy is getting converted to the potential energy stored in the spring. Because finally, why is entirely converting? Why is it? Because the solid mass is finally coming to rest. Because its kinetic energy, whatever kinetic energy it had, is entirely getting converted to potential energy. So kinetic energy of mass is equal to potential energy stored in the spring. That's only possible because finally the ball is getting you know to be at rest. So kinetic energy is half mv square, velocity of the ball squared, is equal to potential energy stored here, which is half k x square, potential energy in the spring. So we can see velocity of the, calculate the force constant. So we have mass is given 2 kilogram, velocity is 10 squared is equal to half into Ka value we have to calculate to displacement is 25 centimeter, 25 into 10 power minus 2 whole square. So 100 into 2 divided by 25 square into 10 power minus 2. So this is minus 4 actually, minus 4. So 200 into 10 power 4 by 625. That is the value of K. So if you solve at K value, you will get it as 3200 Newton per meter. 3200 Newton per meter.
But then how do we know that we have to use kinetic energy and potential energy like?
Yeah. So initially you can see the mass is moving, correct? Initially a mass is moving. Initially you can think of a ball moving. So this ball moving means ball has some kinetic energy, right? You understand that? Whenever something is moving
Yes.
with a certain speed, it has kinetic energy. Whenever something is moving, it has kinetic energy. Now, where is this kinetic energy going? This kinetic energy is getting transferred in the form of potential energy. Why? Because it is compressing the spring. So when you compress, when this ball with the kinetic energy it has is compressing the spring, it is transferring its kinetic energy in the form of potential energy of the spring. So that's why I can equate it. The entire kinetic energy is equal to or is converted to the potential energy stored in the spring. Okay.
Okay.
So now
Sir,
we have, huh? Yes,
sir, why is this kinetic energy is equals to potential energy?
equal to, because whatever kinetic energy it has. Okay, let me think of it like this. So when you are, okay, imagine there is a spring here, there's a spring. Now you are throwing a ball. This ball is having a speed of 10 meter per second. That means what is the energy it is having? Only kinetic energy. How much is that? Half into 2 kilogram into 10 square, half mv square. So this is 100 joules energy is the energy that this ball is having right now. So with this energy, this ball is approaching the spring. Okay, the speed is not changing, but this ball is approaching the spring. Now the ball is here with the same 100 joule kinetic energy. Now when it compresses the spring, it is doing some work on the spring, right? This ball is doing some work on the spring in the process of compressing the spring. Now the spring is getting compressed to, let's say, the spring is getting compressed to this much. Okay, the spring is now compressed this much. Now once the spring starts compressing, the ball is doing some work because of which the ball has to spend some energy. Because if you have to do some work, you need to give out some energy. You have to use the energy that you had in food. So this kinetic, the ball had energy in it, the 10 meter per second velocity, corresponding kinetic energy. So that energy is used up in doing the work on the spring in compressing it. So the spring is getting compressed and by this much displacement, which is 25 centimeter. And who is doing the work? The ball is doing the work. Where is it getting energy from it? The kinetic energy it had. So this entire kinetic energy is getting used up in compressing the spring. It slows down, slows down, slows down, slows down. Finally, its velocity becomes zero when the spring is compressed to a certain degree. So this entire kinetic energy that the ball had, it's becoming zero, and that entire kinetic energy is getting transferred as the potential energy. Why? Because when you compress the spring, the potential energy is stored in the spring. Is that clear, Rehan?
Yes, sir.
So we can say the entire kinetic energy is equal to the entire potential energy now in the spring, because the entire kinetic energy that the ball had is used up in creating the potential energy in the spring.
Yes.
Okay.
Sir, one more thing. In the attendance sheet that you said, my name is not there.
I have talked, so they said, you haven't filled the enrollment form. That's why. It's okay. The center manager will contact you. Once you fill that, your name will come in there. But for now, I'll mention it in the group. Okay.
Thanks, sir.
Yeah. So 3200 Newton per meter, that is the spring constant. Okay, now let's move on to new topics. One more small topic, then we can wind up. Okay, then the spring thing is done. Then we have one two small topics remain, one smaller topic and one a bit larger topic, which is collision, and very important for your school exams. Okay, write the heading. Potential energy of an elastic stretched spring. How do we calculate? By using graphical method. Potential energy of an, write down, potential energy of an elastic stretched spring. How to find graphically the potential energy of an elastic stretched spring. So when you want to calculate the potential energy, first you need to calculate the work done. That work itself is the, stored as the potential energy on the spring. Keep the cameras on, okay? Keep the cameras on, and don't forget to send me the notes after this. So potential energy of elastic stretch spring. We know the spring force is given as F is equal to minus kx. Let's draw a representation here. So let's say this is the spring at its mean position. Okay, this is the mean position. The block is right now at the mean position here. Block is having mass m. At the mean position, this is x is equal to 0. Now, if you draw the graph of force versus displacement, because why am I drawing force versus displacement? Because I know that work done can be calculated from force displacement graph. We have already done that before. Okay, so let's try to draw it. 1 second. Okay. So you can see this is, let's say, the force, spring force, and this is displacement x. This is minus x towards the left and right. Now you can see that when x is negative, meaning what? Meaning the spring is getting compressed. When x is negative means the spring is getting compressed, and the x is less, left of the mean position.
Sir, can you show that spring diagram which you drew with the yellow? Yeah.
So here you can see when I compress it, displacement being negative. So x is negative, that means what is the sign of spring constant? It's already negative here. So the spring constant will be, sorry, the spring force will be positive. Spring force will be positive. So, and if the x is greater than 0, okay, so if it is getting stretched, this is the position, and this is the mean position, x is equal to 0, and this time it is getting stretched, displacement greater than 0. So x is positive, so spring force is negative. So you can see that if you draw a graph between force and displacement, first of all, it should be a straight line. It should not be a curve. Why? Because it's a linear relation. Okay, if it was x square, f proportional to x square, then we will have a parabolic shape. But here it's a straight line because if it's x power 1 is the relation. So you have to draw a straight line now. A straight line, and the graph will look something like this. 1 second. Yes, the graph will be looking like this. So we are assuming that this is the initial position. Initial position is negative. Okay. Okay, so the graph is, you can see that yes. So the graph looks like this. It's a straight line here, like this. Okay. Now, if you want to calculate the work done during an extension process, so if you're stretching the spring towards the right, you just need to calculate the work done. If it is stretched from the mean position to, let's say, some value of x, positive value of x, just need to calculate this work done. Okay, so how do you calculate this work done? Let's say the spring force here is this Fs. Okay, so how do you calculate the work done in this case? You simply have to take the area of that triangle, right? So how do you calculate it? The area of this triangle during an extension of the spring. Only during extension, okay? I'm talking about the extension. And this is area of the triangle shaded region. Uh, Remember that area under force displacement curve gives the work done. Okay, that's what we are using here. So half into base into height, half into x into the spring force. Okay, spring force. So this is equal to half into x into minus kx. Okay, minus kx. Okay, so this is equal to minus half k x squared. So this is the, you can say this is the work done during the extension, which we have already obtained anyways. Okay, so we have already obtained this mathematically using integration, we have done it. So graphically as well, we can calculate it, the work done by the spring force in this case. So this work done itself is stored as the potential energy in the spring, potential energy in the spring. Okay, one more small point here. If you calculate the energy at different points in the spring, okay, so just write a small heading, conservation of energy in the elastic spring. Conservation of energy in elastic spring. Energy in elastic spring. So what does it mean? Suppose I have a spring with this as the mean position, mass m. So here, this is the mean position, x is equal to 0. Suppose I'm stretching it. I'm stretching it to this position and I'm leaving it. So what happens when I leave it? The block will go to the left go to the other side, then come back to the right, come back to the left. So this process continues like this if there is no other dissipative forces. So it continues like this. Okay, so what happens here is that when you leave it, when you stretch it and leave it, its velocity at this point is zero. Okay, velocity is equal to zero at the extreme position. Velocity is zero at the extreme position. Also remember, velocity is maximum at the mean position. Velocity is maximum at the mean position. Velocity is zero at the extreme position. Okay, here as well, if you compress it, go to the other side. So this is also extreme position. In this position also, v is zero. So velocity is zero in the extreme position. Velocity is maximum in the mean position. Okay, and this is the maximum displacement that the spring is having. This is we call it xm, and we call this side displacement as minus xm. Maximum displacement towards the right and towards the left. Okay, so at extreme position, you can see velocity is zero. That means what is kinetic energy? If velocity is zero, zero. If velocity is zero, that means clearly kinetic energy is zero, because kinetic energy is half mv square. So velocity is zero. So the energy that it has, what is the potential energy? Maximum. Potential energy is maximum, and that is half kxm square. This is the potential energy that the spring is having. So total energy that the spring is having is equal to kinetic energy plus potential energy, that is 0 plus half kxm square. So total energy that the spring is having is equal to half kx square. The total energy of the spring, which is equal to potential energy, because kinetic energy is zero. At the mean position, we know the mean position means x is equal to 0, and we are assuming the potential energy is 0 at the mean position because x is 0. So, but kinetic energy is maximum because velocity is maximum. So kinetic energy is equal to half m vm square. Kinetic energy is equal to half m vm square. That is the kinetic energy, and that is maximum. Okay, kinetic energy is maximum. Okay, so you can think of it like this: the entire entire energy that it had is getting converted to the kinetic energy at the mean position. Okay, kinetic energy at the mean position. Okay, so if you draw a graph of energy versus position, if you draw a graph of energy versus position for this spring, energy versus displacement for the spring, when the displacement is zero, mean position, which energy is maximum there? At mean position, which energy is maximum when the spring is moving back and forth?
Kinetic energy.
Kinetic energy is maximum. So we can say this is the maximum energy it is having, and that is equal to the kinetic energy. At mean position, at the extreme position, x minus xm and plus xm. So we can see the graph looks like this. This is the graph for kinetic energy of the spring, kinetic energy of the spring. Why is it curved shape like this? Why is it parabolic? Because the equation has a square term of x. So if there is a square term, it's a parabolic shape. Similarly, if you look at this is the graph for kinetic energy. Okay, please erase this part. Somehow I'm not able to erase it. We will discuss it again. So potential energy, this is the kinetic energy graph. Similarly, if you look at the graph for potential energy, you will see that the graph is the potential energy is maximum at the end, at the extremes. So the potential energy is zero at the mean position. So it's a curve shape like this. So this is how the graph of energy versus displacement looks like. In case of a spring. Okay. So we will compare it with the energy versus X graph of the in the case of gravitational potential energy and kinetic energy.
Sir, we will do it tomorrow.
We'll do it in the next class. But for now, just complete the notes here. Please make sure you're utilizing your time. I know it's still holidays in school, but at least a certain amount of time should be.
So could you explain the graph part again? This graph.
Graph X is equal to 0, potential energy is minimum. Potential energy is minimum. That's why you can see the graph it's becoming 0 here.
Then why the reason why it's like a semicircle and then like a parabola?
It's like a parabola because the graph, the potential energy, what is the value of kx square? So there is an
Yeah.
x square term here. That's why it's a parabolic shape.
Okay, but then why is
So
it also a semicircle?
no, it's not a semicircle actually. It's a parabolic shape.
Oh, okay. Hey, that
Okay,
okay.
it's a parabolic shape. One is upside down and one is like this.
Oh, okay.
This one is for potential energy, this curve, and this curve is for kinetic energy.
Kinetic
The
energy.
upside down one, it's for kinetic energy. This one is for
Okay.
open
Sir,
one is
done,
for.
sir.
Hmm?
I'm done
Sorry.
drawing.
Could you repeat? Yes.
Sir, I finished.
Not audible, Rehan. Can you repeat?
Sir, I finished drawing.
Okay. Yes.
Hmm.
Uh, okay, so we will stop it here. Send me the notes after class, okay?
Okay,
Okay.
sir.
Okay, sir.
Thank you.
Thank
Okay,
you.
sir. Okay.
Okay, bye.